Welcome to the deep dive. Today, we're diving headfirst into a challenge that, maybe surprisingly, often hits the brakes on our most ambitious computational problems. It's the speed of light itself. You sent us some really incredible sources, and they point to this fundamental truth. Even with, an army of super fast computers working together, we keep running into this wall. It's not processing power, it's communication. It's like this silent bottleneck slowing everything down.
That's exactly it.
Yeah.
What you're pointing to, and yeah, the research really shows this vividly, is what we call the communication to computation ratio.
Okay.
Think about it like this. You break a huge problem into loads of tiny pieces for all these different processors. The biggest roadblock, it's usually not how fast each piece gets calculated.
Right.
It's the chatter, the constant need for those pieces to talk to each other, share results, synchronize. And this chatter, this communication overhead, it often grows way faster than the actual work.
Especially if the pieces really depend on each other.
Precisely. If they're highly interdependent, always needing to, talk to their neighbors to figure out what to do next.
So this communication bottleneck, it means for the really complex stuff, we're often just waiting, not actually computing.
Exactly.
Waiting.
And that's why this concept we're exploring today is potentially so revolutionary. Quantum subdivision. It sounds like this, theoretical leap that promises to just slash this communication cost, maybe make previously impossible problems actually solvable.
It really could fundamentally redefine how distributed systems interact. We're
Okay.
moving beyond just faster sums to truly coordinated action. So our mission today is to unpack how this quantum leap could reshape everything, from predicting tomorrow's weather to finding new medicines. Consider this your fast track, to really getting your head around a potentially game-changing idea. Okay, so before we jump into the quantum marvels, let's ground ourselves. Let's really understand the classical problem first. What are some of those big, large-scale problems where communication is truly the silent killer of efficiency, where that chatter is the main thing holding us back?
Well, when you look at classical distributed computing, a lot of the most demanding problems are really handcuffed by communication. Think about large-scale graph problems.
Like social networks or mapping the internet.
Exactly. Mapping the internet, analyzing huge social structures.
Mm.
When you split that massive graph across different computers, different processors, they're constantly doing what's called message passing.
Okay.
Exchanging information about who connects to whom, what the values are, that constant back and forth, that cross-processor talk, it's a major slowdown.
So even if my little corner of the graph is calculated super fast, I'm stuck waiting for a message from the processor next door to know what to do next.
Precisely. You're waiting. Another really prime example is computational fluid dynamics, CFD.
Ah, the weather simulations. Airflow over wings.
That's the one. Modeling weather, airflow, even blood flow. What they do is break down a physical space, like a wing or a weather system, into a grid. Then they assign different subgrids to different processors.
Makes sense. Divide and conquer.
But for the simulation to be stable, to be accurate, those processors absolutely must exchange what's called boundary condition information with their immediate neighbors.
The edges where their grids meet.
Exactly. Without sharing that info, like the pressure or temperature at the boundary, the simulation just, go off the rails,
Yeah.
becomes unstable. It's like trying to draw a huge map where everyone has a tiny piece, but nobody can compare notes on where their piece actually connects to the next one.
Yeah, I can see how that would get messy really fast. What about, like, down at the tiny scale, molecules?
Oh, absolutely. In molecular dynamics simulations, these model how atoms move, maybe to understand chemical reactions or design new materials. If you split the atoms across different processors, calculating the long-range forces, how an atom over here affects one way over there, even if it's on another processor that needs huge amounts of data exchange.
Because you can't just ignore atoms across the boundary.
You can't. Computationally, they're still interacting. And then there are things like large-scale optimization problems.
Like the traveling salesman finding the best route.
That kind of thing, yeah. Or resource allocation.
Mm?
Processors are exploring different possible solutions, and they have to constantly share information about the best ones they've found so far. This helps everyone else prune their search, avoid wasting time on bad paths. But all that sharing, high communication costs, they just pile up.
Okay, so if I'm trying to simulate the perfect wing or design a drug that fits just right into a protein, without this slick coordination, I'm basically just twiddling my thumbs, waiting for data packets to crawl across the network. It sounds like a really inefficient committee meeting. How do these classical systems even try to manage that? You mentioned synchronizing boundary information. What's the magic there? Why is it so vital?
That's a good way to put it, the committee meeting. The magic, as you call it, of synchronizing boundary information is so critical because it applies to almost any big problem you broke down into smaller, connected pieces. Think CFD, finite element analysis, even large geographic data processing. Instead of one giant computer doing everything.
You divide the domain.
Right. Each processor gets its own patch. The real efficiency boost comes because each processor only needs to talk to its immediate neighbors.
Ah, so it's not shouting across the whole room, just whispering to the processor next door.
Exactly that. In CFD, for instance, the pressure on the right edge of my grid piece has to match the pressure on the left edge of your piece, if we're neighbors. By synchronizing just that boundary data, we can both get on with our calculations without waiting for some central command or for information from processors far away.
It's decentralized.
It's decentralized, peer-to-peer synchronization.
Right.
And this drastically cuts down the waiting time, the redundant calculations. Think about the scaling. The core work, the actual physics simulation, might be incredibly complex. Maybe it scales quadratically, ON2, or even cubically, ON3, with the problem size. Gets much harder very fast.
Right.
But the communication, just sharing those boundary values, that often only scales linearly, ON. Grows much more slowly.
Yeah.
So for really massive problems, it's the communication, not the calculation, that becomes the dominant factor, the biggest time sink. It can account for easily 50% or more of the total time spent on these big tasks, just waiting and synchronizing.
Wow. Cutting over half the time just by managing communication better? That's already huge. But, okay, what if we could push past that? Maybe somehow bypass that communication almost entirely. This is where your sources bring up this wild idea of entangled coin flips. Can you walk us through that? What does it mean? How does your telepathy analogy fit in?
Right, the entangled coin flips. It's an incredibly powerful concept for coordination, but it's really important to be clear up front. We're not talking about faster-than-light communication in the sense of sending a message like an email arriving instantly.
Okay, so no breaking Einstein.
No breaking Einstein. The no communication theorem in quantum mechanics still holds firm. You absolutely cannot use entanglement to send classical information faster than light.
So what can it do then, if not FTL messages?
What it does allow is something almost as powerful, maybe more subtle. Instantaneous correlated action.
Instantaneous correlated action. How does that work without sending a message? That sounds paradoxical.
It's about knowing something without being told. Imagine we share a pair of entangled particles. Let's call them our quantum coins. When I measure my coin, say it collapses to heads, I instantly know that your coin, no matter how far away it is, has collapsed to the correlated state, say, tails.
Because they're linked.
Entangled.
Because they're fundamentally linked in this quantum way. So this allows for instant coordination of a choice. My analogy is, if we pre-agree on a rule, like if my coin is heads, I will look here, then when I see heads, I know you saw tails, and because of our rule, I also know you will be looking over there.
The telepathy isn't you sending I got heads, it's that the correlation means you both instantly know the outcome of the shared flip, and thus the other's predetermined action based on that outcome.
Exactly. We've coordinated our starting actions, where to look, or maybe which part of a problem to tackle without a single classical message needing to travel between us. That communication delay is just gone. That is genuinely mind-bending. So if we can pull off this instant coordination, this sort of knowing without being told, what kinds of computational problems, the ones that were previously just too slow or communication-bound, suddenly open up? And, I mean, what's the biggest hurdle? Is it actually creating these entangled states reliably?
That's definitely the biggest practical hurdle right now. Creating, distributing, and maintaining high-fidelity entanglement between distant quantum processors is a massive engineering challenge. But assuming we can do it, the problems that benefit most are those that are highly parallelizable and require tight, real-time coordination between distant parts.
Problems where the pieces are really interdependent.
Exactly. Where subproblems constantly need to know what their neighbors are doing, ideally at the very same instant. Let's go back to CFD and FEA.
Right, the fluid dynamics and structural analysis.
Classically, processors wait for boundary data. With quantum coordination, these entangled coin flips could, in theory, instantly establish the boundary conditions between all adjacent subproblems simultaneously.
Wow, all at once.
All at once.
Yeah.
So all the processors can just start calculating immediately. No waiting for messages. This could potentially make super complex simulations, turbulent flow, detailed weather patterns tractable in near real time. Your sources mentioned, and it's a credible estimate, that over 70% of the total compute time in these fields is currently just waiting and synchronizing boundary info. Imagine erasing that.
70%. That's staggering. And it's not just big physical simulations, right? You mentioned drug discovery, too.
Yes, another huge area is drug discovery and molecular simulation. At its heart, molecular behavior is quantum mechanical, electron clouds, quantum states interacting. Simulating how a big drug molecule interacts with a complex protein involves breaking it down. Quantum coordination could potentially synchronize the states of entangled electron clouds across different parts of that large molecule instantly.
So it's not classical data exchange, it's using the inherent quantum correlation.
Precisely. It's leveraging the non-local nature of quantum mechanics itself. This could enable calculations that are simply impossible today, massively speeding up the search for new drugs. The synchronization of these quantum states, that's estimated to affect over 80% of the computational effort in current approaches.
80%. And there was one more really fast-paced example, finance.
Right, financial market modeling. Think high-frequency trading, complex risk analysis. You need to crunch huge data sets from global markets instantly. Classically, there's always that speed of light delay communicating data between, say, New York, London, Tokyo. It limits how fast you can react globally.
Light speed is the bottleneck.
It is. But with quantum coordination, distributed computers in those cities could potentially know about a correlated market event simultaneously through entanglement. This allows for instantaneous, globally synchronized trades or risk adjustments. In high-frequency trading, that coordination speed is everything. It affects 100% of the efficiency for certain strategies.
This is fascinating. It also raises a deeper point you touched on, linking this instant coordination to intelligence itself. What's the connection there?
Yeah, that's a really thought-provoking angle.
Yep.
The connection comes down to the idea that a core aspect of intelligence is prediction. An intelligent system, whether biological or artificial, anticipates future states or outcomes based on current information.
Okay.
In a distributed computing system trying to solve a problem, this means predicting, in a sense, what the other parts of the system will do or need or where they'll focus their effort. Go back to our entangled coin flip. Both computers instantly know their own result and the correlated remote result. They can simultaneously divide the problem or choose their actions without any communication overhead.
They predict the other's action because it's pre-correlated.
Exactly. This predictive power, knowing without being told, is what eliminates the communication bottleneck. It allows the distributed parts to act more like a single cohesive brain. Instead of waiting for signals between different lobes, they can all start working on their tasks with this immediate, shared, pre-coordinated understanding of the overall plan.
Okay. But this telepathy, this knowing without being told, it can't just work in a vacuum. There has to be some shared understanding, right? A shared world model, you called it, like a common map and rulebook. What kind of maps are we talking about?
You're absolutely right. The shared world model is absolutely crucial. The quantum correlation, the telepathy, is useless without a shared context. A map and a rulebook that let the distinct computers interpret the results of their coin flips and take meaningful, coordinated action. And these maps, that aren't usually physical maps, they're abstract data structures representing the problem space.
Like what?
Well, for instance, you might have qubit connectivity graphs. This map shows the physical layout of the quantum processors and, crucially, which ones can establish entangled links with which others, the who can talk to whom via entanglement. The rulebook here involves the protocols for actually creating and distributing that entanglement reliably. Or, for problems like CFD and FEA, the map is the problem domain grid or mesh itself, the discretization of physical space. The rules, those are the laws of physics that need to be solved at each point on the grid. Entanglement allows each computer working on its piece of the grid to instantly know the correlated boundary conditions from its neighbors.
Got it. And for algorithms?
For complex quantum algorithms, the map could be the circuit diagram representing the algorithm. If the circuit is too big for one quantum computer, you might cut it into subcircuits. Entanglement provides the coordination mechanism, allowing separate quantum computers to run their subcircuits simultaneously and still get a globally consistent correlated result without having to classically communicate the entire massive quantum state between them.
So the map is the problem structure. The rulebook is how the quantum correlations interface with that structure.
Okay. Now, stepping back to the big picture impact, you gave us a really compelling ranking of problems based purely on the percentage of time reduction this entangled coordination could offer. Can you quickly run through those main examples again?
Absolutely. And this ranking really highlights where communication is the biggest classical killer. The gains are highest where those sub-problems are most tightly interwoven. Top of the list. High-frequency financial modeling and arbitrage. We estimated a 95% plus reduction. Speed is literally the only thing that matters here for certain strategies. And classical light speed limits make true simultaneity impossible. Entanglement offers that potential.
95% plus. Almost instantaneous global trades. Game-changing for finance.
Totally. Next up, large-scale climate and weather simulation. Potential for 70–80% reduction. This is huge because it directly tackles that massive bottleneck of synchronizing boundary conditions across vast simulated regions.
Making accurate long-range forecasts may be actually feasible in reasonable times. Potentially, yes. Then, molecular dynamics and drug discovery. We're looking at a 50–70% reduction. This addresses the need to account for those instantaneous quantum effects across large molecules, dramatically accelerating the simulation of complex interactions.
Speeding up the search for new medicines.
Hopefully. And finally, things like traffic and logistics optimization, maybe a 40–60% reduction. By eliminating communication delays, you could make real-time, globally consistent decisions across huge transporter supply networks, optimizing routes and resource allocation on the fly based on instantly correlated information.
Okay, now your sources also touched on something even more, well, mind-bending. This idea from quantum mechanics called retrocausality. The suggestion that, from a certain viewpoint, a future action seems to influence a past event. How on earth does that connect to quantum subdivision? And what are the limits here? Are we talking time travel?
Right, retrocausality. This definitely takes us into the deep, weird waters of quantum foundations, often discussed in relation to experiments like the delayed choice quantum eraser. But crucially, it's not about sending signals back in time. That would violate causality and the no communication theorem. Think of it more as the way we gain information later changes how we must describe the quantum state earlier to be consistent.
So it's about our description, our knowledge, not physical influence backward.
Exactly. It operates on the probabilities, the statistical patterns, not on changing a specific past event. The rulebook, the shared entangled state, is key. It sets up correlations that only make sense statistically when you consider the whole picture, including the later measurements. For our problem subdivision, the link is this. The entangled coin flip essentially creates a shared, predetermined history or agreement between the computers before any measurement. The subdivision decision isn't made in real time via communication. It unfolds according to this pre-existing correlation.
So the simultaneous action feels like prediction because the correlation was already there, baked into the entanglement.
Precisely. It's as if they knew what the other would do, because their actions were always going to be correlated according to the entangled state they shared.
Okay, so given that nuance, is calling it faster-than-light prediction really accurate then for these computational problems?
In the specific context, we're discussing leveraging pre-existing entanglement for coordination. Yes, faster-than-light prediction is, I think, an entirely fair description of the effect. It's not FTL communication, but it is FTL prediction in the sense that one computer instantly knows something correlated about the state or action of a distant computer, bypassing any light speed delay for that information.
Because the knowledge is inherent in the shared entangled state.
Correct. It relies on having that perfect entangled state, the shared rule book for interpreting outcomes, and critically, basing local actions only on local measurements. Yeah, you don't need to wait for a message. If we rank problems by how true this FTL-like prediction aspect is for them, fundamental physics simulations might be at 99%. They're directly mimicking the non-local quantum interactions where this effect is native. Okay. Global network synchronization, maybe 90%. Yeah. Achieving near-perfect anticipation for synchronized actions across a network relies heavily on this instantaneous correlation. And complex optimization problems, perhaps 80%. The ability to instantly collapse towards a globally coordinated, potentially optimal solution strategy without communication lag is a huge part of the advantage. It really does transform the nature of solving these problems from a communication standpoint.
That distinction is important. And you also made another key distinction in the sources differentiating between quantum walks and this instantaneous coordination we spent most of our time on. For listeners hearing these terms, maybe for the first time, what's the core difference?
Yeah, that's a really crucial clarification because the terms sound related but mean different things. What we've been focusing on using entanglement for instantaneous coordination in distributed systems, that's a mechanism. It's about the system architecture and the communication method in distributed quantum computing, DQC. We can call this quantum synchronization or quantum coordination. It's how the different quantum processors coordinate without classical delay.
Okay, the coordination mechanism. What's a quantum walk then?
A quantum walk is an algorithm. It's basically the quantum version of a classical random walk. Classically you flip a coin to decide whether to step left or right. In the quantum walk, you use a quantum coin in superposition. This allows the walker, representing the state of the computation, to explore multiple paths simultaneously through the problem space using superposition and interference.
So it's a way to compute, to search, or explore.
Exactly. It can offer significant speedups for certain types of problems like searching databases or some optimization tasks. It's about the computation itself.
So how do they relate? Can you use both?
You absolutely can. A distributed quantum computer, that's the architecture, using quantum coordination as its communication backbone, could very well run a quantum walk algorithm spread across its networked processors. The entangled coin flips, quantum coordination, provide the framework, the fast internal communication that allows the quantum walk algorithm, the computation, to be executed efficiently across all the distributed nodes. One enables the other.
Got it. Architecture versus algorithm. That makes sense. Wow. What an absolutely incredible deep dive into this potential future of quantum coordination. We started with a really fundamental bottleneck in computing today, just the time it takes for signals to travel, the communication overhead. And we've journeyed through how these, frankly, mind-bending properties of quantum entanglement might offer something that feels remarkably like, well, computational telepathy.
Yeah, and if you connect it back to the bigger picture, it really emphasizes that this isn't just about making computers incrementally faster. It's potentially a complete paradigm shift in how we approach problems that fundamentally rely on massive coordination, often across vast distances. It could genuinely change our capabilities in basic science, in finance, in logistics. Anywhere that synchronized distributed action is key. It's about systems that can genuinely anticipate based on shared quantum states.
And for you, our listener, digging into this, it really forces you to rethink how we conceive of shared information and synchronized action in computation. It's a fascinating glimpse into a possible future where systems just know what the other parts are doing or what they need to do next without explicitly having to be told via traditional signals. So maybe the final thought to leave you with, something to mull over. If intelligence at its core involves prediction, and if quantum entanglement offers a form of instantaneous correlated prediction across potentially vast distances, how might that fundamentally redefine what we even consider to be a single intelligent system, as opposed to just a network of separate computers talking to each other? Could a globally entangled system act as one unified intelligence?